Okay, so let's pick up where we left off. What we're going to complete today is just kind of final things on a link budget evaluation. And then what I'm going to do for the last part of the class, just go through a detailed case example of a link budget for, I believe, KU broadcast system. And then if there's any time left, I'm going to start doing various problems. And what we're going to have today, and then the next class is just working on some problems like the ones you should expect for your midterm exam. Midterm exam is not going to be next class, it's going to be on the following class. So this is exactly 2 weeks from today, because the next week is the midterm. Spring break, sorry. All right, so let's just look at the final remarks here. Some of those I just realized I already talked about, so I'm just going to go quickly. This slide is a little bit misplaced, should have been with the last set, but this again explains the reason for the backup here. There are as we know, there are two types of transponders. There is a band pipe transponders, which everything is analog with them. You essentially take whatever comes into the input of your satellite receiver, you amplify it, and you resend it. And the gain of these transponders is linear in some range of input power. So as indicated here, you know, you have to make sure that you design your link so that the signal that is presented to the transponder falls within this range. If it is within this range, then the amplifier will have the linear amplification. In other words, the signal is going to be whatever it comes out, amplified so many times. If it falls outside of this region, the signal is going to be subject to non-linear amplification. And non-linear amplification is dangerous for two ways, at least for 3 reasons. First reason is if the signal is non-linearly amplified, then the frequency content of the signal itself changes. Right? You start seeing components that didn't exist in the input, frequency components that didn't exist in the input of your signal, and then distorts the signal itself. The second is because of all the intermodulation products, your noise floor goes up. All of these sinusoidals that are particularly third order, fifth order, seventh order products fall within a band that you're operating, and what that does, it creates noise, additional noise. So the fact that you're operating in non-linear region causes degradation of the carrier to noise, right? Because you have component of the noise that comes from self-interference. That's the result of the intermodulation product. And the third thing that is dangerous here is not all the intermodulation products are going to fall in band. Some of them will fall out of band, which means they will be corrupting adjacent frequencies, and that's also not allowed. So what you need to make sure is that your signal is within this linear region. Now the signal itself has its own dynamics. And depending on the particular waveform that you use for the signal, it may have different peak to average power ratios. I explained last time what the peak to average power ratio is. So what you need to do is to make sure that whenever a signal is at its peak, that it's still within a linear region. And that leads to the backup, making sure that your average power is below, so that when the signal is at its peak power, it is still within a linear region of the satellite. Now, for this very reason, in satellite, I don't know if you've sensed that from what we've been talking so far, but link budget is a big deal. You're fighting for every dB. You have huge losses, and then every dB helps. And anything that you can do to minimize this backoff and allow you to operate with a higher transmit power is being done. Now what that means is we favor waveforms that have low peak to average power ratio. Now what that means is you will find a lot of satellite systems working with QPSK, working with even BPSK, working with PSK in general because it's the constant power, working with GMSK, working with the modulation schemes that maintain constant power, right? So that your peak to average power ratio is relatively small. Now in regenerative repeaters, it's a slightly different situation there. You are not amplifying the input signal, right? As long as your input signal is good enough so that you can demodulate it, then you bring it all the way to baseband, clean it up from any noise, and then you always amplify it at the same power, right? So you have essentially two different links. You have transmitter receiver, all the baseband processing, and again transmitter receiver on the downlink. So here, as long as your signal is about some threshold here, then you're fine. You meet your performance requirements. You demodulate the signal successfully, and then you process it and you send it over the same, always with the same power, whatever the power is on a downlink. Now, one thing that I also mentioned last time is that when it comes to the uplink, what is within a view of the antenna is warm earth, right? So there is no background variation in the temperature. What you see here is that temperature of the earth throughout as a function of various latitude, and this is an annual mean temperature. And you can see the hottest areas around the equator, which has the average annual temperature above 30 Celsius. And then you know very well that you can reach up to 80 degrees of latitude. So your variations are 270 to 300 Kelvin. That's the range of temperature. So you're talking about less than half a dB, or at least, or some smaller than 1 dB variations in the temperature. And for the problems that we are dealing with here, we just either pick one of these numbers and do the calculations. And whichever one you pick, the difference is not going to be big. And what is important here to realize the difference, because on the uplink, on a downlink, it makes quite a bit of difference, because depending on what you're looking, your temperature can vary from, what did we say last time, 2.7 kelvins for a black night sky to several thousand kelvins if the sun happens to be passing through the main beam of the receiver planet. Okay. So what are the components of the design? This is kind of following your book. You start with operating frequency, and that matters several ways. It matters link budget, but particularly, and that part we're going to be talking a little bit earlier, your margins are going to be very much dependent on what is the operating frequency, because the different frequency bands have different exposure, I should say, to the elements and variations due to the atmospheric conditions. So then you go and start doing your accounting. You determine communication parameters for the satellite. What is the antenna, the receiver, temperatures, and all that. Then you determine the TX and RX parameter of the ground stations, and start with the transmit side, establish the uplink parameters, find the output power of the transponder, do your downlink link budget, and then calculate the overall signal to noise ratio or bit error rate if you're talking about digitally modulated system. Now, based on your requirements and available margin, you'll be able to calculate outage times, which is telling you what is the reliability of the system. And depending on what the purpose of the system, you may shoot for different reliabilities. If it's TV broadcast, reliability is somewhat smaller, because there is a understanding that if it's really raining and if it's lightning and all that stuff, you may lose a few seconds of the TV signal. But if it's some important telecommunication satellite that carries the backbone, then backbone traffic, then reliability needs to be high. higher. And then if it doesn't meet the requirements of the reliability, then you go back and see where you can make trade-offs. You know, can I increase my antenna size? Can I put more power? Can I cool the front end of my receiver? Can I, even to the point, can I relocate my hub points and do all sorts of designs to make sure that you meet the coverage and reliability objectives. So that's kind of, in the book you have a few more paragraphs on each one of these steps. What I'm going to do now is just go through an example of a KU band distribution, TV distribution system, and just kind of go slowly through all of these steps and make sure that we understand all the calculations that are involved. So let me do this. So this is example KU band TV distribution system. So when we say KU band, we're going to have a pair of frequencies. We have downlink, which is 1145 gigahertz, and this is paired with the F uplink, which is 14.15 gigahertz. As we expect, the weaker link gets lower frequency, so the downlink, the link from the satellite, gets to operate at a lower frequency band. How does this system look like? Well, you have a big station here on the ground that is connected to some, I guess, data center, or I would say content, where the TV programming is put together. Like you put all the channels, you know, together and into what happens to be a broadcast. This signal goes all the way to the satellite. Satellite would receive the signal and then broadcast this signal to the coverage area on the globe, right? And this would cover, obviously this is on a sphere, but I'm kind of just drawing this as a general concept of the area. And this would be your point on axis, but then you're going to have a whole bunch of usually, you know, smaller satellite receivers that are usually of a low performance, right? These are your VSAT systems. The VSAT means very small aperture terminals. The antennas are relatively small and placed on the roof of houses or buildings or wherever you want to receive the signal. And there is really no return link. You just have a unidirectional. It's a broadcast. So this feed carries all the channels. These channels are all sent, and then wherever you put the dish, you should be able to point to the satellite broadcast and get the signal. Now you still need the decoder and all of that, but that's a secondary concern for us here. Usually we specify some contour over which we claim that we provide the service. For the purpose of this example, I'm going to say whatever is encompassed within a 3 dB contour, I'm going to claim that this is the service area. Now, this is somewhat arbitrary, but not that arbitrary. You cannot say whatever is minus 10 dB contour, because then the guys on the outskirts are going to have very poor coverage, right? And usually what you do is when you do your link budget, you dimension it so that the users on the outskirts of the coverage area have the reliability that you require. If you happen to be within a main beam, then you have a slightly better reliability. Now the problem with the coverage contour, if you remember the video, a lot of our target areas are not circular, or that they don't have some regular shape. So there's a lot of design that goes into the antenna on the satellite to properly shape these contours so that you maximize the I guess the size of the coverage area, making sure that the energy that you're sending from the satellite does not go into the areas where there's nobody to receive the signal, right? Because that's just a waste. Okay, so this is the general settings. Let me get the parameters. KU satellite. Obviously, when you talk about TV distribution systems, you're talking about geostationary satellites. This is the satellite that sits on top of a given area, and it appears stationary from that area. So all the TV broadcast satellites are on the geostationary arc. And if the satellite is on the arc, what we typically just what we provide as a description where it is, we just say what is the longitude of the satellite, where on that arc it is. So this particular satellite is going to be at location 73 degree west. So it has 28 KU band transponders. Total RF output, total power is 2.24 kilowatts. Antenna gains are 31 dB, both TX and RX, and then on axis, right? And so this is within the main beam, right? So that's the key thing here, because you have to compensate for the fact that you're both this guy here, this hub, and your users may not be within the main beam of your transmit and receive antennas. The system noise temperature on the receive side, of course, is 500 Kelvin. You know, a portion of that is contribution from the Earth, because you're receiving from the hot Earth, but the rest of it is contribution from mostly front end of your receive. So this is a system noise temperature. And I'm kind of simplifying it here. You know, usually you would sit down and calculate it for a given set. The saturated power, so this is is 80 watts per transponder. And the transponder noise bandwidth is 54 megahertz. Typical bandwidth that you find in bandpipe transponders are 36 megahertz, 54 megahertz, and 72 megahertz. These are the most common. There's nothing really that prevents you from using other bandwidths, and sometimes certain satellites use, but most commonly in practice you're going to find these, and historically this goes into TV channelization and how many TV signals and all that it can transpond. Signal that so this is a KU satellite. Signal that is being sent here is compressed video. And what we know about it, it is rate is 43.2 megabits per second, and C to N required overall is 9.5 dB. So what I need to do is, you know, when I provide the signal at any one of these ground stations, I have to make sure that its carrier to noise ratio is better than 9.5 dB. So that's a signal. Earth station. This is TX Earth station. So this hub here. So this is TX, and these are all RX stations here. So TX station has an antenna diameter. Has a diameter of 5 meters an efficiency of 0.68, just to refresh those formulas that we used to estimate the gain of these antennas. Location on the contour is -2 dB. And additional uplink losses or miscellaneous uplink losses are 0.3 dB. And then RX earth station has the following parameter. The system noise temperature is actually, antenna noise temperature is 30 K. This is antenna. Front end LNA has a noise temperature of 110 K. The location -3 dB on the contour, and noise bandwidth, I guess it's the noise is 43.2 megahertz. I have here so I have a whole bunch of other parameters. Let me just put it here for satellite. C2N on the uplink is 30 dB requirement, and back off on a power amplifier is 1 dB, and then and then I have reliability stuff, so rain attenuation. It says your reliability here is 0.01% of the year. And that gives you uplink margin of 6 dB and a downlink margin of 5 dB. So those are the margins. Why are they different? And why is the downlink margin lower? Well, two reasons. They may be at different areas of the globe, but they also have different frequencies, right? And the higher frequency typically have higher margin requirements. And then the last clean air loss for uplink, that's 0.7 dB, and for downlink, 0.5 dB. So there's tons of data here, you know, and I assume that the author kind of listed all of these so that you can see what are all the things that can appear on your link budget spreadsheet, right? You know, so I guess in any particular scenario, you would spend some time and catalog all the gains and losses. So I'm going to leave this data on a board and kind of use this part of the board to work out the link budget. So first, let's look at the uplink. The requirement we have, following that what I gave on the slide, is to provide 30 dB on the uplink. What I'm going to calculate first, and this is the easiest thing to calculate is, in this link budget, is the free space path loss. See how much of the free space path loss I have. I guess here, distance to the satellite, distance is 38,500 kilometers. So free space path loss is 92.44 plus 20 log of the frequency given in gigahertz, which is 14.15 gigahertz, plus 20 log of the distance given in kilometers, so 38,500 kilometers, and this gives me 207.2 dB. Very large path loss. So it is bad. Now, C is, I'm going to count, so I have a C to N. What is it that I'm after here? Let me just, in the link budget, remember that the thing that I need to determine is what is the power that I need to provide here, right? C1. And that's essentially your receiver sensitivity. What is the power that I need to provide? So we calculate kind of backwards. You start from the C to N requirement, then the next thing I'm going to have N, and then based on C to N and N, I'm going to calculate C, and then I know the path loss and antenna gain, so I work it all the way down to the ground transmission to determine what is the power that I need to transmit, because that's the know by turn, right? That's the one that controls the overall performance of the uplink. So let's calculate the noise on the uplink. So noise in dB watt is going to be your 10 log of KT system times the noise bandwidth plus, that's it actually, there's no noise figure here. So this is 10 log. Now what is the system? This is, K is 1.38 times 10 to the minus 23 joules per Kelvin, times the equivalent noise temperature of 500 Kelvin, and times the noise bandwidth, which is 43.2 times 10 to the 6 hertz. So that's the noise bandwidth. Why is the noise bandwidth different than the bandwidth of the transponder? So this is transponder, not the noise bandwidth. Noise bandwidth is 43.2. Why is there a difference between these two? Right? The transponder has allocated bandwidth, and that comes from the frequency plan for a given band. Let's say we have taken over the entire band when we separate it into channels. In this particular case, the channel has 54 megahertz, but we don't really utilize from end to the end. You kind of put your signal in here, right? It looks like this, and then at the IF you actually filter it with a filter that has that has the skirts towards the edge of the band. So even though you have 54 megahertz reserved for the transmission, not all 54 megahertz is contributing to the noise, right? The filter, the channel filter here determines that the noise is coming from not 54 megahertz but slightly smaller band. So when you calculate this noise,
that particular bandwidth would have to be given, right?
yes. That a lot of these come given to you as a system engineer, right? Somebody sits down and designs just a waveform, and somebody sits and designs just a channel filter, right? That you're going to use. So all of these are coming as an input data. So when you calculate this, this is minus 125.26 dB watt. So that's the noise floor against which your signal is being received. And if you need to maintain signal to noise of 30 dB in the uplink, then you're going to have then you can calculate your required signal power as C on the uplink in dB watt is going to be your noise in dB watt as your floor, plus you have to be C over noise on the uplink expressed in dB. Right? That's how you calculate what we essentially call the receiver sensitivity. So in this case here, this becomes minus 125.26 dB watt, plus your C2N requirement on the uplink of 30 dB, and this gives you minus 95.26 dB watt. What is this value? This is the value that you need to provide to the input of the receiver. So this is after the antenna of your cell. Okay? So now we can put together the lead budget for the uplink. We can say that the C on the uplink in dB watt is going to be whatever is your transmit power times the gain of your transmit antenna at the earth station. How do we call these two together? EIRT. And then minus free space path loss, and then minus LA, which are your, I guess, additional losses, and then plus the gain of the receive antenna at the transponder. Excellent transponder. So if you look at all of these quantities, you kind of trying to balance the checkbook. We have determined what this number is. We know what this number is. We're given this number and this number as well. And then what we need to determine is these two guys together. Now to determine these two guys together, we don't know the actual gain of the transmit antenna, but we have a good way of estimating it from the size of this antenna and from the efficiency that we have. So I'm going to continue here to use a little bit more of a board. So the gain of the transmit antenna is nu times d squared over 4. So that's the effective aperture of the antenna, and times 4 pi over lambda squared to translate the effective aperture into the gain. So another way to write this is nu d squared over 4 d squared pi, right? Pi, right? Because d is the diameter, right? So there's d squared pi over 4 times 4 pi, and then times c over f, so you have c squared times f squared. Either one of these equations can be used to estimate the gain of the antenna. In our case here, if I substitute the values, this becomes 0.68 times the diameter of the antenna. Or let me do it this way, because I want it in dB. So let's say this is 10 log of 0.68 times pi squared times pi squared divided by 4. Actually 4 and 4 I can cancel. So nothing right here. I can say 3 times 10 to the 8. That squared and times frequency squared, which is 14.15 times 10 to the 9 quantity squared. And when you calculate this antenna gain, this is 55.72 dB. That's a huge gain, right? This is antenna with a very large gain. And you know, why is that gain large? Because the antenna is large. The antenna has a diameter of 5 meters, but also it is large relative to the wavelength. Wavelength is very small. They're operating at 14 gigahertz, which means that the wavelength is this big, right? Half a centimeter. So now that we have the gain, then we have everything in this equation here except the transmit power. So if I substitute all the, let me just substitute here. I can say that this is, from here I have minus 125.26 dB watt. That's your C uplink is equal to the transmit power plus this gain, which is 55.72 dB, minus free space path loss, which is 207.2 dB, and then minus LA, which are okay.
Additional losses, right?
Yeah, but let me, I messed up here
95.
somewhere. This is not 125.
No,
What
it's
should this
95.
be?
95.
Yeah, there you go. It is this value here. Minus 95.26, right? 207. Minus, I have here 0.3 plus 0.7, which are the losses of the miscellaneous losses that I have somewhere here listed. These guys, and then uplink losses of the air, and then plus the antenna gain. But the antenna gain of the receiver is 31 minus 2 dB. Why? Because I'm locating my my earth station, transmitter station, at a minus 2 dB contour relative to the axis of the satellite. So that's the gain. It's not really 31 anymore, but 29. And now this is essentially just the budgeting equation here. So from here, the only unknown is what the transmit power needs to be. And then I easily calculated here the transmit power needs to be 28.22 dB watts, which is 664 watts, right? Which is a relatively high power, but I have one feeding station, the earth station, so you can afford it. If you need to reduce it for some reason, then you can work on some of these parameters. Some of them you can work on, but some of them, most of them are given, right? Because this is, you cannot change the free space path loss or the losses in the clean air. The only really thing that you can work on to impact the link budget is the size of your antenna, or if you're in an early stage design, maybe you can work on reducing the noise figure of your front end amplifier, because this 500 Kelvin may be not count by some amount, because you know that only about 300 is the contribution from that comes through the antenna, and the rest of it is the contribution from the front end amplifier. So that's the parameter we determine on the uplink. This is how much of the power on the uplink you have. You need to provide so that you meet the C2N on the uplink of 30 dB required for the communication. Any questions here?
Could you add the margin in?
Well, the way how this example is worked out, you first work clean air, and then we're going to check what happens if you have. It's a little bit of iterative process, as you can sense, and as such, you would. I'm doing it right now so that you understand the equations, but almost all the time, when you say to somebody do a link budget, what that means, sit in front of the Excel and enter all of these equations into Excel, and then you can play with parameters and see how you balance it. So this is uplink. Let's just go and work on do the same analysis for the downlink. If I set so the bottom line here is, if I set my power to 28.22 dB watts, then I'm going to have 30 dB of this carrier to noise at the receiver of the satellite transponder. So let's look at the downlink budget. Now downlink is looking from the satellite down to the ground. Here are the things that I know. PTX on a downlink in saturation is 80 watts, which is 19.03 dB watt. So that's the power that I can transmit from the satellite. But that's the maximum power. The backoff needs to be 1 dB. Therefore, really PTX maximum is going to be 18.03 dB watt. So that's how much I can transmit on average, and don't run into nonlinear part of the power amplifier. Part B, let's determine EIRP for this transponder. So this is going to be your transmit power plus the gain of the transmit antenna and minus your contour, right? Delta gain. This is a contour relative to the on-axis gain, because we are now dimensioning not for these guys that are in the center, but for the guys that are on the outskirts of your coverage area. So in this case, this becomes 18.03 dB watt plus the gain of the antenna, I believe it was 31. Yeah, 31 dB. And minus 3 dB, so because you're at the edge of the contour, and this gives you a value of 46.03 dB. Now we already now what comes next? Free space path loss in this case is 92.4 plus 20 log of 11.45 gigahertz, sorry, plus 20 log of the distance, which is 38,500 kilometers, and this gives me a free space path loss of 205.33 dB, slightly lower because we are at the lower frequency. Now this signal travels down to the Earth station. At the Earth station, we have to do the same calculations we did for the satellite. We have to determine its sensitivity. Right? So,
I have a question. The 80 watts is per transponder. So,
yes, per transponder.
So is that ERP per transponder then?
Yes.
So you need to, in the end, multiply. So you
Yeah.
go for one transponder, so the entire satellite, it would be 28 times.
24. Right.
28.
I think it's
28. 28. Okay. 28 times this 80 watts. Would that fit in a total power budget on the transponder? We need to check that. So, but you do calculations per transponder, right? And you assume that each transponder is the same.
Okay.
So now, so I calculated here. Okay, so let's do the sensitivity at the ground. So noise in dB watt is going to be your 10 log of K T system times the noise bandwidth. So this becomes 10 log 1.38 times 10 to the minus 23 joules per Kelvin. And then your overall system temperature is going to be your antenna's temperature, which is 30 K, and then plus the temperature of the front end, or RF front end, which is 110 K, and then times the noise bandwidth 43.2 times 10 to the 6 hertz. And this gives you an overall, the noise floor for the receiver there, which is minus 130 dB. Okay, so, I didn't specify. What I'm doing a design here, the receive Earth station, I want C2N to be 17 dB. Oh no, so that's the, sorry, again, this is the overall target all things. So how do I say all? That's the one that I would like to maintain. So if I would like this to be the overall C2N, then do this here. I know that the C2N for both links is going to be 1 over C2N for the uplink plus C2N from the downlink, 1 over those. Right? C2N all is 17 dB, which in linear domain is 50. C2N on the uplink that is provided by my design is 30 dB, and this is 1000. Right? So I need to actually calculate how much of a C2N on the downlink I need, and I'm just going to substitute in here. So I have 50 has to be equal to 1 over 1000 plus 1 over C2N. And then from here, we calculate easily C2N downlink is going to be 52.63, which is 17.21 dB. Right. So just let me, because I went through this relatively quickly. The overall design requires that in clear air, I maintain C2N of 17 dB. So that's trying to accommodate for these margins that I'm going to test afterwards and see if I meet the requirements. Now, from what we derived last time is the overall C2N is given through this averaging equations that where both the C2N on the uplink and on the downlink figure into calculating the overall link. In this case, you have two links which are quite different. One of them is at 1000, and the other one is at 50 linear, 30 dB and 70 dB. So the overall is really determined by the weaker one of the two. Now that I know how large C2N on downlink needs to be, then I can calculate what is the required signal on a downlink. Let's say F here. C on a downlink is going to be whatever is the noise on a downlink in dB watt plus C2N on a downlink. And in our case, this is minus 130.79 dB watt, and then plus whatever is the 1721 dB. So this gives me the signal power that I need to have on the downlink, which is neg 113.58 dB. Okay. So that's the C on the downlink, and then we're going to put the overall equation that will allow us to calculate what is the gain of the receive antenna? Right? What is the gain of these antennas? That's the unknown parameter here in this say that C on a downlink is going to be IRP on your transponder in dB watt minus your free space path loss minus your antenna losses plus the gain of the received antenna. And if I substitute here, I get minus 113.58 dB watt. dB watt is equal to EIRP. I calculated at 46.03 dB watt minus the free space loss, which is 205.33 dB, minus these losses here, which is 0.5 plus 0.2. Where are these guys coming? 0.5 is these losses, and what is 0.2? It's, I guess, somewhere in the page.
Yeah, downlink loss. Miscellaneous downlink loss.
That's miscellaneous downlink loss. That's in the book, right? So this gives you plus the gain of the receive antenna, and then from here we calculate that the gain receive antenna off axis needs to be 46.43 dB. But that means on axis it needs to be slightly large. Okay, so that's how you approach all of these things, and it's as I said, not really hard. You just have to be patient and make sure that you don't forget something. Now let's see what happens if you dimension the system this way. Then what happens in the clear sky conditions? You're going to have 17 dB of the C to N for the stations that are located on the edge of the coverage area, right? So let's see now what happens when you experience rain. So first, let's look at what happens when there is a rain on the uplink. Okay. The rain on the uplink, what happens in that case? Only additional attenuation. Right? Because the temperature of the rain is the same as the temperature of the earth. Therefore, what you're viewing from the satellite receive antenna does not change in the temperature. So the system temperature will not change in this case. What you're going to have is an additional attenuation, and your losses increase from 0.3 dB in a clear sky, I guess, or not 0.3, 0. I guess 0.7 dB to how much? To 6 dB. Okay. Is this, I don't know, maybe this is. So now, since the losses go to 6 dB, then your C to N on the uplink decreases from 30 dB to 24 dB, right? Why? Because as a result of the rain, your signal decreases, but the noise temperature stays the same. Right? So your C to N will just be hit on a C side. Assuming that the transponder has a fixed gain, then your transponder power transmit now becomes 18, what was it, 18 dB watt, 18.03 dB watt, minus this 6 dB, so it goes to 12 dB watt. Right? And so therefore the ERP on a transponder becomes now from 46 becomes 40.03 dB watt, 6 dB reduction. And then as a result, C on a downlink is now smaller by 6 dB uplink. No, C on the uplink I already took into account by recalculating this value, right? But now, as a result of this value, assuming that your transponder has a fixed gain, then your EIRP on a transponder becomes smaller, and as a result, there's a 6 dB reduction in your EIRP, and as a result, there's a 6 dB reduction in your downlink signal as well. So your C on the downlink goes from, what was it before, minus 113.58 to, I guess decreases from minus 113.58 dB watt to minus 119.58 dB watt. Right? And then looking at your C to N on a downlink only becomes minus 119.58 dB watt minus the noise power, which we calculated to be at minus 130.79 dB watt. So this is 11.22 dB. And then your overall C to N, all, which is that 1 over C to N on the uplink plus 1 over C to N on the downlink, works out to be around 11 dB, right? Which is greater than 9.5 dB required for the signal transmission. So here's the first observation. When it rains on the uplink, right, it rains on the downlink too. Why? Because the signal, if you have a transponder that has a fixed gain, right? Because the signal attenuates on the uplink, and but it also, because the gain is fixed here, the ERP is lower, and therefore it impacts your overall link budget two ways. Now let's take a look at rain attenuation on now down. Rain on the down. So here the rain has two effects. First, additional attenuation. That is by 5 dB. and then rain changes the temperature, system temperature is changed. Now the sky temperature, the front end will not change, but the sky temperature will change to be n times 270 times 1 minus 10 minus 8 over 10. Right? That's the equation that we mentioned the last time. Is this the right equation? I think I'm following the example as it's given in what happened to 30K.
One minus 1 over the attenuation.
Yeah, that's that. So yeah, I'm afraid that I wonder if in the book he also forgot. You would have to remember here. I have two components, right? I have this 30K, and I have the front end 110K. This the presence of the rain will remove some of this, but this will still be there, right? But I guess it's neglected here. We need to look at what the explanation for that is. So let me just continue this way, and then we can correct next time if I look at this. So what this ends up being is, assuming this is close to 1, this ends up being 194K. So the overall temperature from the sky now becomes 194K, and the system temperature becomes 194K plus the front end guy, which is 110K, which gives you the system temperature of 304K. So that increases the noise. So their effects are twofold here, but they're both on the downlink. It will decrease the signal power, and it will also increase the system noise temperature. Now, repeating the same calculations as I had initially, this gives me C on the downlink of minus 118.56 dB watt. And it gives me noise on the downlink now different, which is minus 127.42 dB watt. And this gives me C to the N on the downlink of just 8.85 dB, which gives me C to N overall equal to 8.82 dB, which is smaller than 9.5 dB. So in this case, having a rain on the downlink actually causes some outage. And where is that outage going to happen? It's going to happen for some of these guys, on the outskirts. They don't have, your coverage contour is going to shrink some, right? Now, in this particular example, the design is done deliberately to protect the uplink much more, right? The design is so that you have 30 dBs on the uplink, right? 30 dBs on the uplink. It is important to protect your uplink, because if the uplink goes down, meaning if the uplink is not closed, then there is no broadcast, right? All of the receivers will not work. So in this example here, it is acceptable to have, I guess, the way how it's worked, to have some outage on a downlink, as long as the uplink is serving the majority of the users. Now, this, the way how I just did it is rarely done that way. What I have included, and I would like you to do that before the next class, there is a spreadsheet that actually has all of these numbers that is in the folder with the class. And it kind of implements all of these equations, and I think it's much more accurate than what I did here on the board. And it will allow you to see what happens when you change some of these parameters and how you can do various trade-offs. Now, what we have, and I mentioned it, the big part of the link budget evaluation in general are these numbers. And this is what we need to explain in a very near future. How are we getting these numbers, right? This will allow you to, the spreadsheet that is over there allows you to experiment and see what happens, with different links if you change these numbers. But very soon after the midterm, we're going to go and address how these numbers are determined.
Just a quick question. Why do we worry about system noise temperature on the downlink side, but not the uplink? We increase
the system noise temperature on the uplink stays very much constant, right? Because regardless of whether it's raining or whatever is, the earth temperature does not change much. Earth is in the main beam of the antenna, and whatever is the temperature of the earth is kind of what is experienced by the antenna. In that case, the background does not change. And the overall system temperature on the uplink consists of majorly two components, whatever comes through the antenna and whatever is the front end of your LNA. And both of them don't change. On a downlink, the situation is different because, absence of rain, you're looking at clear sky, right? So the temperature changes, and you can change, as you can see, from order of magnitude, so the difference is significant. On the uplink, it changes the fraction of the dB. So, thank you. Okay, any questions? Go through that spreadsheet, and kind of go through this example again, and then find the lines in the spreadsheet that address these particular things, and then kind of make sure that you understand how it works.